Hello, everybody. Welcome to this week's Alex Does Legal. Yeah, these things get repetitive after a while. So I'm still trying to find my cadence, trying to figure out how to present myself on stream. It is a journey, I can tell you that. Well, today we don't have a lot of time because I have a lunch appointment in about 40 minutes. So we're gonna dive right in. And today we are gonna work on a let's try one of these. Let's try one of the medium ones. I think the medium ones have been pretty good to us. So let's try one of these medium ones. I'm gonna pick one of the snazzy sounding name, container with most water. Let's proceed and see how that goes. Upgrade the dynamic layout. Oh no. How about no? Thank you, LeetCode. I'll think about it next time. Alright. As usual, we're gonna start by looking at our question. It says here container with most water. You are given an integer array height of length n. There are n vertical lines drawn such that two endpoints of the ith line are I0 and I height. An array height of length n. So I see. It's a one-dimensional array. It's a one-dimensional array which contains a bunch of numbers. And these numbers represent the water level. Okay, find two lines that together with the x-axis form a container such that the container contains the most water. Return the maximum amount of water a container can store. Gotcha. So there are two parts here. Well, first, let's think about what this question actually means. Because I think the question is not extremely obvious about what a container is. Let me close. About what a container is. So basically, imagine if you have a line like this, okay? And then you start pouring water. Let's say it starts raining, okay? It starts raining, and your sort of this thing fills up. So let's imagine we're in a two-dimensional space. All these things are lines, like six, right? Or you can imagine like a three-dimensional bucket. A three-dimensional bucket, and all these lines become like let's say you put a little board in between, right? These blockers, these walls are of different height. And let's say it starts raining. So it starts raining, water starts to fill up, and our job is to determine the pair of containers, the pair of lines that basically contain the most water. Well, let's be clear. Let's look at this example a little bit and break it down a little bit. Okay, so look at this pair right here. For instance, this red line, this is a 0. So this shorty over here is 0, and then the tall red line is 1. So between 0 and 1, you would in theory fill up just 1 unit of water, because water comes down here. The height of water is the height of the lower side of the wall, obviously. So water fills up here, up to this line here. Can you see my cursor? I don't know if people can see my cursor. How do I draw? I need a thing that can draw. Okay, anyway. Water comes up to this line right here on the 1. And because the two lines are one space apart, the total amount of water is just 1. Okay? So we learned two things here. Basically, one is the water contained between two walls is at the height is of the shorter wall. So if your shorter wall, this one right here is only 1 unit tall, and the other one can be as tall as you want, it doesn't matter. The amount, the depth of the water that this pair of walls can hold is just 1. It's based on this guy. Okay? 2, the width of the water is the distance between the two walls. Okay? The width of water is the distance between two walls. So the total volume of water that can be trapped within wall 0 and wall 1 would be 1, because that's the distance between them, times 1, which is the height of the shorter wall. So this is 1 unit of water right here, this square here. Okay? So we have to maximize both of these things. Now look at this one. This is the correct answer here. You have these two red lines. They are both fairly tall. The depth of the water that these two red lines can trap is going to be 7. It's basically the height of the shorter line. One is height 8 and the other one is height 7. So the amount of water it can trap is going to be the height of the shorter line. Now, there's one thing that we'll be very careful about, which is we can't just find the pair of lines. We can't just find the two tallest lines in the list. Because look at this, check this out. This is 0, 1, 2, 3, 4, 5, 6. So between 1 and 6, 6 and 1 are the two tallest lines, right? So you would think that 6 and 1, since they are the tallest, and they can trap water of depth 8, they would contain the most water. But that's not true. Because remember, the volume of water actually is the area of water, technically. It's the height times the width. So 1 and 6 can trap water of depth 8. But the distance between them is 5. So that's 8 times 5, which is 40 units of water. Whereas 1 and 6, 7, 8, 1 and 8 can contain water of depth 7. But the distance between them is 1, 2, 3, 4, 5, 6, 7. It's 7 units. And that gives you 7 times 7, which is 49. Okay? You can't find the two tallest lines. Need to take width into consideration. Okay? So that's the tricky thing about this exercise. That's the tricky thing. So basically, what we need to do is to find every pair of lines. Okay, we're going to start with a naive method, which is find every pair of lines and then calculate how much water there is between them. Okay? We're going to start with the naive method. Naive approach. Check every pair of lines. Okay, we're going to do that first. And I'm going to think about what the more clever approach would be, because I'm not super sure what the most clever approach would be. I think it would use some form of dynamic programming, but I'm not sure. I will think about it. But let's start with this one. So for I, let's say left, and we know this already. So we know that for loops in Python, we can use range. So height, length of height. So we're going to iterate over all the lines in height. So we take left is in X range, line, or right in range, left plus 1 to height. So notice, so as a reminder, the notation here, basically this says the way range works. When it's given one argument, it goes from 0 2 argument minus 1. Okay? Or let's just call it x minus 1. So when given 2 arguments, it goes from x to y minus 1. When given one argument like this, range x, comma y. Sorry, it's not a colon, it's actually a comma. Okay, this is kind of weird. It got me a bunch of times the first time around, because in the first case, the first argument x is actually the end of the range. In the second case, when given 2 arguments x, again the first argument is the beginning of the range. So this is a little bit, it sort of makes sense, but it doesn't make all that much sense to me, to be honest. But it is what it is. We're gonna just roll with it. So left to right, we have a way for calculating how much water there is. So here so this is actually good programming practice, just in general, to put small intuitive units. So you have a concept is small intuitive units. Let's just call it calculate water, and it takes 2 numbers, and you want to calculate the water between them. Oh, so it takes 4 numbers. So left index, right index, left height, right height. Okay? So what you want to return is, we're going to assume that left is always smaller than right, just to make things a little bit easier. Is we want to get the difference in the index. So that's the width of the water multiplied by the minimum of the height. I always forget this. Python min function, is it math.min or is it just min? Yeah, you can just do min. Okay, so this is how much water there is. So we have to return how much water there is, right? We don't have to actually return what the left and right index is. Max water equals 0. So in the event that the height is 0, or there's only one thing in the height, which I guess they promise us is not possible, maximum amount of water is 0. So that's going to be our default. Let's call it my water equals to calculate water, left index, right index, left height, right height. Okay? If my water, or I can make this even easier, max water equals to max of max water, comma my water. Now return max water. Okay, so this, I'm pretty sure this should work, but it's not the most optimal way to do this. Okay, so it works, but it is slow. It is slow because let's think about what the time complexity of our solution is. Okay, calculating water is an ON operation. It's the most complicated operation that we have mathematically, but it is still an ON. It's still an O1 operation. All right. So this part is O1. And how many times we run this O1 block of code? We run it n, which is the length of the height, times n. So we have an n squared complexity O n squared. This is not great. Okay, this is not. I wouldn't say it's bad. In all honesty, let me just move my face here, so I'm out of people's ways. Okay, in all honesty, this is not a bad way, but I want to think about what clever way we have of making this a little bit faster. So if you think about it, let's say I am here, right? I'm this line right here. Let's say I'm this line right here. I want to find a line that is as far away from me as possible and as tall as possible. Okay, so we know okay, cool. Okay, gotcha. Okay, here's what I'm thinking. And we got to think this through together, my friends. Because I don't know what the right answer is. So let's say okay. So there's two components to the water area, right? There is the width and then there's the height. So let's say we begin with maximum width. We have left equals 0 and right equals you guys see my hands? Okay, left equals 0. Oh man, this is weird because I'm flipped. So my left is different from your left. So left equals 0 and then right is the end of the ray, right? So we have the widest possible configuration we have. So in this scenario, how will we improve? So how will we improve on this scenario? We can improve on this scenario if and only if we go to a wall that is taller than one of the two walls than the shorter wall we have. Than the shorter wall we have. So if the wall is not shorter, we're done. Right, so okay, let me sort of explain my strategy. My strategy is like this. Instead of testing every pair of walls, we sort of do this ON square thing. I'm shooting for ON. Okay? And the way I'm shooting for ON is as follows. I have two pointers on the left and the right side. And I want to sort of get them to close in. Close in on each other. And as I close in, I'm going to be it's going to be strictly worse. Okay, let's do one wall again. Let's switch strategy a little bit. Let's do one wall at a time. So let's say I'm starting with this guy here, this short guy. My wall on the other side is this tall guy. I'm going to go from this cannot possibly be better from right to left, this cannot possibly be better than the ones we have seen before, okay? So his best wow. I should not have picked medium today. Now I'm stumped. Let's see. His best sort of pair would be this one because it's the furthest away. It's the furthest away. And because everybody's taller than him. It's the furthest away, and everybody's taller than him. So there is no way, right? There's no way that you'll find anybody better. So this is his best candidate. So so first of all, I can skip anybody who's shorter than me. I will only move my pointer if I find somebody taller, right? So now my initial pointer left is at 0 and right is at 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. Yeah, so 8. 0 and 8. And now, because left is... This guy is taller than me, so I'm going to move forward. So I'm going to move by 1. I'm going to move by 1. And so my best so far is this guy right at the end. Okay? My best so far is this guy right at the end. So, well, actually one easy heuristic we have is that, you know, because we're moving from left to right, right? Because our left pointer is moving from left to right, the width gets smaller each time. So if the current best left I've seen is of height, let's say X, there is no way another wall that is shorter than X or equals to X is going to be better than me. To be better than my current value, I only need to test walls that are taller than me. Yeah. So that actually gives you a bit of a savings right away, but it's still O n square, because then you have lines that goes up just in a triangle. So let's write that out. Best left equals to 0. Okay. Now I have to actually do this. If my water best left equals left. Okay. So now every time let's just go with -1. If best left was -1, so best left has a value, and best left height of best left is greater or equal, or rather height of left is smaller or equal to best left, the height of best left. So basically, this is a situation where my best left so far is this guy, and then I move on this guy. This guy is shorter than him, right? So there's no way. I don't even have to check the rest of any of my rights. I can continue here. So if height of left is smaller than height of best left, so the new guy is shorter, I can continue. So this makes it a little bit faster. Let's check if it's correct. Speed up. Yeah, it's still correct. It's actually even slower than before because the amount of speed up that I get from here is not extremely high. Okay, so this one would have an extremely good speed up. This one will actually run much faster with my .26 than without this. Without this, this should run much faster. Then again, it's 26 milliseconds. Yeah, okay. Anyway, this is one way to speed it up. What other ideas we got? Okay, so left moves towards the right. We can sort of apply the same strategy to right. We can sort of apply the same strategy to right. And say, so this is the best left. Because the same strategy applies, right? Right is moving towards the middle. And if right has to get taller, you know what? Let me sit on this for a while. Let's sit on this for a while. Let's sit on this for a while. I'm gonna think about it some of the time because I have to go. All right. Well, that's it for today. Thank you, guys. I'm sorry it's been a letdown. Well, it's not a letdown. We did come up with a naive solution. But let me think about what the better solution should be. And we'll talk about it next time. Until next time, everybody.